Hello everyone. Welcome to SZ4Grads for webinar series. So my name is Hagur from the University of Wisconsin-Madison. I'm today's webinar's host. So this webinar is organized by SZ4D and SZ4Grads. So let me first briefly introduce them first before I introduce today's speaker. SZ4D stands for Subduction Zones in 4 Dimensions, which is a community-driven initiative for a long-term interdisciplinary research program to understand the limits and possibilities of predicting geohazards in subduction zones. SZ4Grads stands for Subduction Zones for Graduate Students and Recent Graduates, and is a network within SZ4D for early career researchers studying subduction zone processes. So there are also several things I want to mention today. First, I want to remind that the presentation is being recorded, and will be posted on our SZ4D YouTube channel for later watching. And also the live translated captions are available, so you can turn on this option if you want. I want to make some advertisement for our SZ4D, some activities, SZ4D activities at the upcoming AGU in December. So let me first copy the link. Okay, I think Yuron has already copy link to everyone. So there on December 8th, which is Sunday, we have a mini workshop. On December 8th, we also have also on Sunday we have a SZ4D icebreaker, and also on Wednesday, December 11th, we have an event at AGU Town Hall, and at Thursday on December 12th, we have a SZ4Grads launch, and yeah, just please click this link and to look at this event. And if you are interested in them, please register for them and come by then. All right. Thank you. All right, so let's move on today's talk. So first, it's my honor to introduce the speaker, Dr. Xiaochuan Tian. Xiaochuan is currently a postdoc, I think working in geodynamics at UC Davis. He got his bachelor degree in geology in 2013 from Zhongshan University, and he got his master degree in geophysics in 2015 from the University of Memphis, and his PhD degree also in geophysics in 2021 from the Columbia University. And from 2021 to 2024, he was a postdoc researcher at the Boston Boston College. And I think starting from this October,
exactly.
he has been working at UC Davis as a postdoc research fellow. So okay, let's welcome Xiaochuan for today's talk. The title of his talk, I think, is Numerical Simulations of Clinopyroxene fabric development under lab and natural conditions. Is that still right?
Yes. So I essentially that's what I'm planning to talk about, but I have some updates, so including some basically what I've been doing at Boston College.
All right.
Yes.
Xiaochuan, it's your turn.
Thank you very much, Pao, for your kind introduction. Thanks, SZ4Grads, for this great opportunity for me to present 2 projects that I did at Boston College with Professor Mark Bain and other collaborators. So first of all, my name is Xiaochuan. As you can see, the English spelling is a bit long, but the Chinese character is very simple. And if you look at Chuan, it resembles 3 rivers flowing down the hill. So it means actually river. And I think I would like to introduce that because it's a blessing name for me, because the river that connects the ocean and the mountains. To me, it's a great name, I guess, to study earth science. As you can see, today's talk title is Deformation Across Scales, from play boundaries to lab experiments, with slightly updates from the original one. And these, I'm planning to talk about 2 projects that I did at Boston College. Actually, the 2 projects are of very different science question. One is about oceanic transform faults, and the other is much smaller scale lab experiments. And so I tried to ask ChatGPT to find a good name, good title for me to include all these science science questions. And I think it did a great job. This is what you're seeing earlier, deformation across scales. So one keyword is deformation. For both play boundary question and the lab experiment question, deformation and related geometries are the focus of my work. Scale is another keyword, as it ties the 2 together. Today, we will see 2 examples that varies in space from 100-kilometer play boundary to lab experiment that deform a sample the size of your thumb. We'll also see they vary in time from thousands of millions years to seconds and days. And then finally, before I get started, I would like to say that please feel free to stop me and ask a burning question during the talk. For questions that may lead to longer discussion, I do plan a 10 minutes or so discussion toward the end. So for the play boundary problem, here is the only textbook I use for preparing my qualifying exam that I was able to finish within a month under the pressure of preparing the exam. And it turns out to be my favorite textbook, Earth Portrait of a Planet by Stephen Marshak. And in this textbook, it describes 3 types of play boundary: divergent play boundary, mid-ocean ridges, convergent play boundary like subduction zone, and transform faults. So I am curious about what's the type of deformation and what topography will be resulted from different deformation. For example, at global subduction zone indicated in this map by these blue lines, the major types of deformation is this kind of reverse faulting, and one plate going above the other, and then the subducting oceanic plate going beneath the continental ones. And what types of topography it will generate? If we take a look at West Pacific, like at the Mariana Trench, specifically at this Challenger Deep, it is the deepest point on Earth. You can immerse the whole Mount Everest into this trench, and there's still some water above it. And what about at global divergent play boundaries, like the mid-ocean ridges indicated by these red lines? The major types of deformation is via normal faulting. So the hanging wall will slide down relative to the footwall. And one type of feature, so-called the abyssal hills, which are probably the most common tectonic feature on the surface of the Earth. You can see these linear oceanic hills that's parallel to the mid-ocean ridge axis. And what about the third type, the transform faults? And I was curious about the numbers of previous studies that have been done on each type of play boundary. So I did a Google Scholar, and it quickly showed me that turns out the subduction zone ranked the first. It got 285,000 papers. but transform fault only has 55. It's almost only 20% of that of subduction zone. So when it's understudy, that means there is opportunities. So let's take a look. Here's a global map again. Now the red lines indicate the oceanic transform fault that segments the mid-ocean ridges. And a fun fact is, if you sum all the length of the oceanic transform fault, it turns out to be a value of 48,000 kilometers, which is even longer than the circumference, equatorial circumference of the Earth. And along these kind of plate boundaries, the textbook described that there is no new plate form and no old plate is consumed. So before I work on this project, I thought these kind of faults are a conservative plate boundary, but what's the topography arise from this kind of deformation is the main focus of the project. So if we have now let's take a bird's eye view or map view of typical oceanic transform faults. This is one mid-ocean ridge. This is another segmented by this oceanic transform fault. If we so one plate is moving to the left and the other plate is moving to the right. So the two plates are constantly moving opposite direction relative to each other. And so all the deformation are accommodated by this oceanic transform fault. If you take a cross-section AA prime for looking at its topography, turns out it's not that simple. There are three types of topography arise from this simple strike-slip plate deformation motion. It ranges from small ridge to a small valley to a deep valley. And so what controls the topography of this kind of oceanic transform fault? And after 2 years of study, we finally published a paper earlier this year, and we have this one-sentence summary. The answer is it's the magmatism that controls the global oceanic transform fault topography. This work is done with collaborator from University of Hawaii, Professor Gary Ito, and postdoc Jana Schwartz, as well as researcher from Germany, Geoscience Mainz, Boris Kaus and Anton Popov. So let's first take a look at the data. Revmeyer in 2021 studied globally 41 cases of oceanic transform faults, and they carefully analyzed the topography, not only along the transform fault, but also the adjacent fracture zones that has no relative plate motion, as you can see indicated by these red, yellow arrows that move in the same direction as compared to the transform fault that the two plate moving against or in the opposite direction. And what they did was that they tried to plot the transform fault topography or depth below the sea level as a function of the associated mid-ocean ridge velocity spreading rate. And what they find is, surprisingly, as the spreading rate of the associated mid-ocean ridge increase, the transform fault depth also becomes shallower and shallower. For example, at slow spreading mid-Atlantic ridge, the marathon transform fault. Here is the map view of the topography. You can see mainly it's in a blue color, so it's more than 4 kilometers beneath the sea level. Plotted here is the average topography of this fault. This is the profile when you're making cross sections and then sum them up and take the average. So you can see the relief, the valley relief is more than 1 kilometer in depth, and it's white. But if you move to faster spreading Southeast Indian Ridge at 88 East, you will see a bathymetry look like this. Now the color is redder, so it's shallower, and the valley is smaller, it's less than 1 kilometer in relief. Further, if you move to fast spreading East Pacific Rise, when you do the same practice, now instead of valley, you start to see a small ridge. And overall, the average broad scale topography is the shallowest among the three. Now we plot them together. So as the spreading rate increase, the valley, the topography changed from deep valley to small valley to shallow ridge. One thing to note is that the fracture zone for the intermediate and fast cases are not valley. They are pink color. As compared to slow spreading cases, the fracture zone are also valleys. So the first question is, what control this global systematic that show shallower topography is associated with faster spreading rates? Another global systematic was shown by Grefmeyer 2021 is that when they plot not just the transform fault topography, but also the fracture zone topography adjacent to the transform fault. So the vertical axis now is the fracture zone depth. Horizontal axis is still the transform fault depth. If they are at the same depth, they will plot on this dashed line. However, most of the cases, even all of the cases show shallower fracture zone than their associated transform fault, on average by about 700 meters. So this is our second question: why there's such a depth difference for all spreading rates? And to address that questions, we built a 3D numerical model, and we used the code LAMEM. So within a box, we implemented the plate separation on each side with a spreading rate of Vx. And then within the box, we simulate two mid-ocean ridge dike opening that's being offsetted by this transform domain. And as the stress build up, the transform domain will undergo plastic deformation. And so then we can quantify the topography arise from this deformation. This model is built on top of Buck et al. 2005 and the decades of other works that focus on studying how the magmatic and tectonic processes interact with each other for the mid-ocean ridge topography. And the key parameter M is the ratio between the amount of dike opening over the amount of far-field plate spreading. When M is equal to 1, that means all the plate separation is accommodated by magmatic processes. There's no stress built up and no fault will occur. However, when M is 0, all the plate separation has to be accommodated by this kind of normal faulting or more complex tectonic deformation. What we did is that we add this dike opening in not just at the mid-ocean ridge, but also inside the transform the space between transform fault and fracture zone inside this transform ridge transform intersection. And we call it MT for transform fault to distinguish it from the previous work. And this is not just by imagination, but also based on observation, like bathymetric evidence for magmatism inside this ridge transform intersection. You can see these hook ridges indicating magma processes. Also, this is inspired by much earlier work where Carson and Dick, they show from deep tow camera at the ridge transform intersection these dike separation and pillow basalt, indicating a lot of volcanism and magmatism, magmatic processes going on within this zone. Another observation constraint we have is by seismic. So when people do seismic lines across a fracture zone, in general, at slow spreading cases, they show a shallower moho or a thinner crust. And as we know that the other constraint we can have is from gravity. One parameter is residual mantle bouquet anomaly, RMBA. And this number is a proxy for crustal thickness because the crust is less dense than the mantle. So when we have thin crust, the gravity observed on top of it will show a higher anomaly than where you have a thicker crust. And Greg, 2007, did a global systematic analysis of transform fault as they did an analysis of residual mantle bouquet anomaly across all different spreading rates. And they look at the difference between the transform fault and the ridge plotted here on the left vertical axis. So when it's positive number, that means the transform fault will have higher RMBA indicating thinner crust. Whereas when it's negative, that means the transform fault will have thicker crust or than the associated ridge. And so they show a systematic that with faster spreading cases, the crust of the transform fault is generally thicker or with a lower RMBA indicated on the left as well from the bathymetry. But if you look at slow spreading cases, you will see thinner crust or deeper bathymetry. All these observations inspire us to link the velocity of the associated mid-ocean ridge spreading to the amount of magmatism, because RMBA is scale inversely with spreading rates, and spreading rate is associated with the crustal thickness. And so we can link the crustal thickness with the proxy for magmatism, MT, because MT, the magmatism has been shown to be associated for scale with the spreading rates. And with this, we can start to look at some model results. When our MT is less than 1, in this case 0.96 or 96% magmatic within the transform ridge intersection domain with 4% of tectonic extension, we will see a deep valley arise. And also the fracture zone is a valley. But when MT is around 1, we see the fracture zone is no longer a valley and the transform fault valley is shallower. When MT is further increasing to 1.08, the transform fault turns into a small ridge. Now, when we plot all three together and look at the cross-section topography, we'll see as MT decrease, the topography changes from a small ridge to a small valley to a deep valley. And here we plot the model result against the earlier observation for the 3 cases. So the model also not only reproduced the transform fault topography, but also the fracture zone topography, as you can see here. So as you remember, probably the previous global observational constraint of the systematics of transform fault topography that becomes shallower with faster spreading rates. Here is our model results. The trends, the models capture the general trends of shallowing of transform faults with faster spreading rate or higher MT. So for the first question, why the transform faults become shallower with faster spreading rate? Here is our one-word answer. It's the magma. It's the spreading rate dependent magmatism within the oceanic mid-ocean ridge transform fault intersection. And now if we look at along the transform fault rather than across the transform fault topography, you can see all 3 cases show deeper transform fault than its adjacent fracture zone. And for the second question, why all the fracture zones are shallower than their associated transform faults, here is our model results. This is a surprise because we were not actually trying to model this, but turns out the results show not just qualitatively, but also quantitatively similar to what we observed, that the fracture zones are shallower by a few hundred meters. So for the second question, what's the cause? Let's try to take a thought experiment. Imagine we have a perfectly weak transform fault and we were magically able to pin a rubber band across these transform faults onto the 2 plates, A at A0, B0, because there is no shear stress. As the plates offset, the rubber band will be just cut into 2 without connection, and they will just advect away from each other without any deformation. However, now imagine we have a perfectly strong transform fault that allow no relative offsets. And then we do the same, pinning a rubber band on each side. And now we add a cross section and to indicate how it would deform. So on the left, this is moving into the screen, and on the right, the plate is moving toward us. As the 2 plates move away from each other, the rubber band will be lengthened. They are rotated and also lengthened. This lengthening generates tensional stress that pull the pre-weakened transform fault apart, generating valley. And so as you keep offsets, this valley will increase in depth. And this is supported by the model results plotting here with the topography or bathymetry. And then these arrows are the principal tensional stress. So you can see these arrows are rotated and then are pulling this transform valley apart to generate this valley. One thing to notice is that these stress are not across the fracture zone. That's one big reason for why the transform fault is deeper than the fracture zone, because the fracture zone has no relative motion and there's no such shear-induced tension stress. So to summarize this first part, we have mainly 3 points. magmatism is what really control the global broad-scale oceanic transform fault topography. And then the oceanic transform fault are not conservative plate boundaries, and plate motion change is not necessary in order to for transform fault to have a topography. And I would like to take some questions for about 2 or 3 minutes before I move on to describe the next one. If you have any question.
Yeah, I do have one question about, so you say
Yes.
in the transform fault with fast spreading rates, there are more magma, right? That's why
Yeah.
you have a relatively shallow valley. May I ask why there are more magma in fast spreading rate, like transform fault region?
Yeah. Great question. You are really touching the root cause now. Actually, we are not sure about the ridge transform intersection magmatism, whether it's coming from along the mid-ocean ridge. So for slow spreading ridges, we have gravity data indicating the magmatism focus at the ridge segment center and then propagate along the ridge to maybe then they reach the ridge transform intersection. But for fast spreading cases, the magmatism are much more continuous and homogeneous. And so the how those magma get there is indeed a very good question. But to the first order, from previous studies that look at the mid-ocean ridge processes, as you have faster spreading, you will generate more decompression melting from the upwelling mantle, and that's where you got more melt. But at the ridge transform intersection, it's a lot more complicated. So I think it's a ongoing work. But for slow spreading cases, if the magma are sourced from the ridge segment center, then for sure they will get a lot less magma toward the tip than the fast spreading cases. All right.
Thank you.
Yes.
Thank you to answer. And there also one question in the chat.
Okay.
I need to first read the question. Oh, you can read the questions.
I can see it. Yeah. So someone say, do these results change depending on the length of the transform fault? If it is short or large offset between, that's a great question. So we actually did sensitivity test, and the result is we didn't do exhaust all the cases, but we did 30 kilometer and 60 kilometer long, and they plot along the same trend. So at least for the parameter space we explored, they didn't change much. But I can imagine for 100 kilometer, like the equatorial Atlantic, the situation might be very different and much more complicated, which will require further investigation. Also see Jeremiah ask, so are these estimates of effective coefficient of friction across the transform faults, and are they systematic different or for slow and fast spread? So are these estimates of effective coefficient of friction across the transform fault, and are they I think that's a great question. So in terms of the mechanical strength of the transform fault and friction coefficient, so in the model, when we do this, we just assume a friction coefficient, and we did change that to see its effect. What we find from our model is that when we have, let's see if I can find that plot. So we did systematic study in terms of the strength of the transform fault. When you have higher friction, we see a general trend of deeper valley. And one very interesting observation from seismology is that the earthquake B value, which can be can be a proxy or maybe can reflect the strength of a fault, show consistent result that you will have deeper valley at the same spreading rate. You will have deeper valley when your B value is lower, if I remember correctly. Lower B value might mean stronger fault. From Schroth's GRL paper, maybe 2012, I forgot exactly the date. But in terms of the nature, in terms of what's the strength, it's a very complicated, and we don't know for sure, as there are a lot of serpentinization and hydrothermal processes. Yeah, so it's definitely ongoing work, and very interesting one too. Yeah, thanks for the question. Yeah, thanks. So looks like there's no further question. Let me move on. I guess we need to end at noon, right? How or?
Yes, you can move on.
Okay, yeah. So my second part is ongoing work and has not been published yet. So I will show you some exciting preliminary results. And this part will not go long, probably 15 minutes. So the second part is with these collaborators from UCSD, Hui, and GFZ. And we're looking at numerical simulations of Clinopyroxene fabric development in Greek's apparatus experiment. So our scale really switch from very large kilometer, 100 kilometer to finger thumb scale. And the time scale also shrink from million year to seconds and days of lab experiments. The big picture question is to better understand how continental crusts grow over time. So here's a plot. The vertical axis is the number or the volume of continental crust, and horizontal axis is time. So time go from the origin of the Earth from the right to current at 0 year. And initially, the crust grow quickly, and then it generally gradually slow down. But even today, there is still growing crust. Yeah, so in the beginning, people think it might be a magma ocean, so there's no continental crust. So our focus today will be mainly toward the end, or what is toward current day. How does the crust grow? So one way that the crust grow is at the arcs. So at the subduction arc, there's a lot of arc volcanoes. These are fed by magmatism generated beneath. And this magma will intrude and erupt. Part of them will accrete at the bottom. And people think it's by this continuously fractionation process where the denser, more mafic material accreted at the bottom will detach and resink to the mantle, leaving behind more felsic and less dense, more buoyant parts at the surface. that continuous fractionating process will generate more and more continental crust. So the why it's called arclogite. So the part that's removed and sink back to the mantle are called arclogite. And for you can see arc means the location. Logite, it comes from the rock, is mainly eclogite. And so why eclogite, why they delaminate? Because eclogite are very dense. They're mainly formed with mineral like pyroxene and garnet. And their density could be even denser by 10% of that of underlying mantle. And current example is Colorado. So back in time, the flat subduction slab Farallon extend beneath the current Colorado plateau. And due to magmatism, it formed at the subduction zone shown previously, the crust will grow, become thicker and thicker. And also accreted beneath are these green arclogites that will, some of them already sink back into the mantle. Some are delaminating right now. One paper by Lavender et al. 2011 showing from seismic tomography that if you do a cross-section A prime across the Colorado Plateau, you will see this high velocity anomaly, looks like a drip. And they're interpreting that, so it's right beneath this Y dash area. They interpret this as the ongoing delamination of the arclogite. One very interesting observation is that around the Colorado Plateau, there are actually a lot of volcanic activity. And these are the age of all the volcanic eruptions. So you can see they form a ring pattern that shrink in radius, become smaller and smaller toward the center. And they bring up xenolith to the surface where we can have a direct analysis of the deformation, those deep crustal and mantle rock in terms of that deformation history. One example are these xenoliths that carry clinopyroxene. Looks like here. And when we study the crystal prefer orientation from these xenoliths, we can see clear fabrics. So before I jump into the results, let me quickly introduce you what is CPO, because it took me 2 weeks to really understand, but hopefully in 1 minute I can show you what it really means. Imagine I am the person, I am a crystal, my head is pointing in the A-axis, and then my front belly is the B-axis, and my left hand is the C-axis. Now, I'm standing inside this room where the floor is this line. So my A-axis is pointing up and down. My B-axis pointing toward you. And my C-axis is left and right. If I am under a lot of stress, what I will do? I will lay down to relax, right? So my head is now pointing left and right, indicated by here, and my belly is still pointing toward you, but now my hand is pointing up and down. So in the Greek apparatus experiments, they will compress the sample indicated as yellow here with high pressure and temperature. And this is a quick video to show what will happen. And also this is the sample size. It's a similar size of your thumb. After it's compressed, the sample will look like this, where it bulge outside. Let's take a quick video.
Representative results of Carrara marble deformed at 700 degrees Celsius and 1.5 gigapascals are shown here. This includes a scheme of the deforming sample assembly and the stress versus time curve produced during the deformation experiment. At first, both the pressure and temperature are increased alternatingly during the pumping stage. While the sample assembly is heated by using the Joule effect, both rams transmit forces to actuators and pistons that pressurize the sample assembly. When the target pressure and temperature are achieved, a period of hot pressing is applied to sinter the sample, if applicable. Then, the sigma-1 deformation piston is advanced, moving through the lead, and then pushing on the alumina piston to deform the sample. This describes a hit point, followed by an elastic then plastic curve during the deformation stage. When deformation is stopped, the temperature is quickly dropped and the pistons are moved back, so that pressure is slowly decreased to preserve microstructures. After the experiment, the stress versus time curve is corrected from friction and rig stiffness to calculate the total strain and differential stress prior to characterization by analytical techniques. This type of experiment can also be performed with non-coaxial geometry, as shown here, for an olivine aggregate deformed at 900 degrees Celsius and 1.2 gigapascals.
So under this kind of Greek apparatus experiment, they can do axial compression and also shear. So for a clinopyroxene, the xenolith rock mineral fabric that's carried by volcano eruption to the surface, they also did lab experiments. So under compression, they formed this so-called S-type fabric where the B-axis will show up and down point maximum and girdle in C-axis. So girdle is just basically mean you're pointing in all direction that towards you, left and right, like scanning like this. And when it's undergoing shear deformation, it will form a low strain L-type fabric, a girdle like this, and then point maximum left, right. And then, but when you are undergone high strain, the B-axis will be up and down, and C-axis now become left and right. In addition to this pole figure of fabric, geometric fabric, they also can study the rheology of the clinopyroxene by this flow rule. So the N is the power of the overstress, and A is the prefactor, Q is activation energy, R is gas constant, T is temperature, epsilon dot is strain rate. So N, A, Q, R are mineral specific, and temperature, stress, and strain rate are what we can control and change in the experiment. When we fix temperature, we can change the strain rate and measure the stress arise from that. And we rearrange this equation and take the natural log. We can see N become the slope of this linear plot between strain rate and stress, which shown in the next slide here. So here are the linear lines of different temperature, and arise from that are the slope, which is the power N, which they get to 3.5. Another way to do it is by fixing the strain rate, but changing the temperature and measure the stress. Again, now we can see the slope. By calculating slope, we can get the activation energy Q, which is shown here. So the slope now is the activation energy value, 310 kilojoule per mole. Now we can plug in these lab results into equations to extrapolate to all kinds of different conditions. For example, in here, we just rearrange that flow rule. We can get a relationship between the viscosity eta as a function of temperature at the bottom axis. And so when the temperature becomes hotter and hotter, at natural strain rate 1e minus 14.10 over seconds, the viscosity will become lower, and so the material is weaker. But when we increase the strain rate to lab condition, the viscosity is a lot lower. So that gives us this motivation for this study. So basically, the viscosity as a function of strain rate, if the lab can only cover these strain rates, but the natural strain rate are much slower, there is a gap that's that we cannot connect. And so the goal is to use numerical models to first benchmark the lab result, and then we extrapolate to natural condition to see how the slower of strain rates will affect the result. And the other methods in terms of how we calculate fabric development is shown here. We don't have the time, but I'm happy to discuss further with you later on. And this is the model results. When we do the axial compression, all the geometry is one-to-one to the lab setup. This white wireframe are the deformed sample. So here's a video. Initially, it's like a sandwich. It got squeezed, pressed vertically, so it bulged out. And all the dots are the particle that we track the fabric development. And the longer the axis, the arrow, the more integrated strain it has. And the arrow pointing toward the B-axis point maximum. So you can see here are the other results. So the top pole figure show the leftmost particle, and then the middle one, the third one show the middle one. And let's compare with the lab experiments. The model reproduced the main feature of this S-type fabric under axial compression, a point maximum in the B-axis and the girdle in the C-axis. Now, if we do shear experiments, here's the video. When the top aluminum oxide shear to the right relative to the bottom, you can see all these particles tracking the fabric development, and also the sample become thinner and it's sheared. And the fabric result is shown here. So, but one thing to mention is that it has actually spatial variation. The middle one is able to generate or reproduce the best fabric as compared to the lab results. So to notice here, the fabric are rotated by 45 degrees because the setup geometry is 45 degrees to that of the horizontal. So to bridge the gap, if we do lab experiments under much slower strain rates, here's the result. You can see if we do a whole lifetime of 70 years of researcher under that strain rate, the sample almost deform nothing. So that's why we really need this to bridge the gap. And here is the result that run to 270,000 years. You can see the sample deform qualitatively similar to that of what we've seen earlier for the lab strain rate. And these are the results of shear deformation. And here we compare the two. So on the left is natural strain rate, and on the right is lab strain rate. Qualitatively, they are pretty similar, but you can see there are some finer detail difference, which we're still working on quantifying them. And here, let me summarize this project. So basically, we developed new direct algorithm for the slip system that's able to implement not just one type of mineral, but general to all crystal structure. We implement the CPX, the Clinopyroxene slip system into directs, and we also build a new 3D numerical model for Greek apparatus. And we can keep track of fabric development of these experiments. And now we're testing and trying to bridge the gap between the lab and nature. That's what all I have. Thank you so much for your time listening to my stories.
All right. Thank you so much, Xiaochuan, for the excellent talk. So
Thanks.
let's would like to open for Q&As, although you already answered some questions. Yeah, let's see. If you have any questions, please type them in the chat. All right, so I think I can ask one more question about your first part of your presentation about the shear-induced tensor. You talk about the relationship between the shear-induced tension and the topography. Is it right?
Yes, that's right.
Like, could you briefly like talk again about their relationship? I'm curious. My question is, isn't the shear-induced tension released by the earthquakes? Right.
Oh,
Yeah.
yes. That's a great question. That's a great question. Yes, the tension will be released by earthquake that basically released. The energy will be released by an earthquake. So the stress will become lower again after an earthquake happened. So, but the thing is, the two plates will be constantly moving toward the opposite direction of each other. So the stress is continuously being rebuilt up. And also there are probably places where the earthquake wasn't able to rupture through, because as we've seen from seismic studies that a lot of time the earthquake are patchy. They didn't rupture the whole transform fault. So at where the earthquake wasn't able to propagate through, the stress probably is still there to generate this shear-induced tension. If that kind of answer your question.
Yeah. So yes, I think so. So my follow-up question: if you consider the tension being the shear tension being reduced by being released by the earthquakes, will your results change a lot, or just there won't be any apparent difference?
Yes, that's a great question. And actually, I haven't thought through about that. But one thing I would like to notice is that the deformation is plastic. So what generates the topography are plastic deformation, which will not go back when the elastic stress is decreased. Maybe that's one thing that will not, but probably part of the topography is held up by elastic strain. We don't know, but maybe it's not huge as compared. I mean, it may be much less than the plastic deformation generated topography. That's my hunch, but we need to really investigate in order to have a quantitative answer.
Got it. Thank you.
Yes, thank you. So
Yeah,
I see Jeremiah, another question from. So for the mid-ocean ridge transform faults in your models, do you apply fixed strain rates to the two plates to simulate divergence? In the case of plate rotation in nature, is the plate strain locally approximately orthogonal to the ridge axis? What about in the model? Oh, these are all very good questions. So first of all, in our model, the divergence, we did apply fixed stretching velocity on the on the so it's a 3D box. So we apply, let me get to this, apply constant stretching velocity on two sides, and the strain rate inside the box is self arise. So from the equation that we solve, so the inside the strain rate actually is not constant or homogeneous. It changes in space and time. And in the case of plate rotation in nature, is the plate strain locally approximated orthogonal. Actually, quite a if you look at Mark Bain's paper, Bain et al. 2002, they look at the focal mechanism around retransform intersection, and some other papers also show that actually the normal faulting or normal earthquake focal mechanism rotated. So away from the RTI intersection, they are mostly orthogonal to the ridge axis. But when you get closer, actually the focal mechanism can rotate quite a bit. And they are kind of consistent with this stress where the normal faulting become, rather than left-right, they kind of doing this oblique rotation. And yeah. Oh. Let's see another one. Oh, yes. Thank you. Thank you for the good question.
Maybe I can ask one more question. So you, in your second part, you talk about the numerical simulation lab experiment. I'm not studying. I'm not doing any lab experiments. So I just have a general question. What's the most difficult part for doing this experiment?
You mean what's the most difficult part of this study?
Yeah, for you. No, for doing the lab experiment, because I have no experience.
What's the most difficult part for lab experiment?
Yeah.
Yeah, to be honest, I haven't done any lab experiment as well, but I was blessed to be able to have chance to consult a lot of real experimentalists in how they do this. And so I don't know what's the most difficult part. I think yeah, I don't know, because I have no experience at all about doing this experiment. Yeah. But I'm very interested in trying to do some in the future, and I will let you know what if I got some chance.
All right, thank you.
Yeah.
So let's see if other people has any other questions. Okay, all right. So if there's no more questions, let's thank Xiaochuan again for his excellent talk today, and also don't forget to register for the SZ4D activities at the upcoming AGU meeting via the link copied in the chat. And thank you everyone for attending today's webinar, and goodbye and take care. See you next time.
Thank you very much, Hao. Thank you, Yurong and SZ4Grads.
Okay, bye.
Bye.